main research field concerns the study of inverse problems in vibration with applications to structural diagnostics and structural identification in mechanical engineering and civil engineering. This is a quite young or recent topic if compared with well-established subjects in structural mechanics. And I would like to explain the main features of this topic, and in particular to explain the meaning of the word inverse. So let us consider a simple structural system, which is this glass, for example. And suppose that we want to reproduce this experiment. We want to determine the vibrational response of the glass due to some input. And well, for this kind of problem, there exist, well-established techniques to determine the answer if the glass is, the shape of the glass is known, if the material forming the glass is known. For a given input, we have established well-known methods to determine the output. But this is a typical prototype of the so-called direct problem in vibration. However, there are some applications in which the situation is completely different, important for practice. For example, we could have only a partial knowledge of the mechanical properties of the material, for example. In this case, we can repeat the same experiment, exciting the glass and measuring, in this case, the answer, in order, in this case, to deduce some information on the mechanical property of the system. So we measure the input-output, so-called input-output relationship, and we want to deduce information on the system. This is a prototype of the so-called inverse problems in vibration, in which the input is known, the output corresponding to that input is measured, and we want to deduce information on the system. Of course, this is a very simple example, and application to real-world structures are more difficult by several reasons, because the more complex modeling, the necessity to define some structural details, difficult to model in practice, to induce the input, which is not easy, to take into account of experimental errors and so on, but the core of the problem is this one. And just to conclude, I would like to say a few words concerning the main difference between inverse direct problem in vibration. Usually, direct problem in vibration are well posed in the sense of RMR because the solution that exists is unique. It depends continuously on the data. For inverse problem, the situation is different. Usually, the solution is not unique and depends very weakly with respect to the data. And concerning these two main properties, uniqueness and the stability of the solution, a lot of research has been developed in the last 30 years. And we're working on these two problems, both from, say, the analytical, mathematical, and applied point of view in the last 20 years, more or less. Concerning application of inverse problems, I can say that there are two main goals. The first one is the improvement of existing mechanical model of a system, as we have discussed a few minutes ago. The second goal is more closely related to damage detection. So detection of damaging structure by dynamic data. And even for this case, in order to explain the main idea, I would like to take the simple example, the simple structural system we have considered before, this glass. But in this case, in two different configurations. As you can see, this is an undamaged glass, and here we have a damaged one. And so we can try to repeat the previous experiment by measuring input-output relationships between the input and output for the undamaged and damaged glass. As you can see, for the same input, we have different responses, different vibrational responses between the undamaged and damaged glass. And the main point in damage detection methods is first of all to determine the difference, the change in the mechanical behavior, in the dynamic behavior, as secondly try to give an interpretation of this change in order to identify the damage, to see where the damage is and how big is the damage. This is the main idea. Of course, the application to real-world structures or even medium-scale structures such as beams, frames, rotors become more complicated by several reasons, we can say. But the main core of the problem is the following. In the last 30 years, a lot of research has been developed on this topic in the scientific literature, and one of the main problems is essentially that one can find in practical applications is related to the low sensitivity, usually, of the mechanical properties of the system with respect to the damage. And on this topic, we worked a lot in the last 20 years, both for general point of view, both for medium-scale structures, say, and also to large structures such as buildings, and more recently, in the last 10 years, bridges. Here the situation is much more complicated, but the main problem is that we have discussed right now. University Carlos III de Madrid is focused on the development of dynamic methods for damage detection in structures. This is a joint work, a collaboration with the Spanish colleagues, in particular with Professor Lourdes Rubio of the Department of Mechanical Engineering and Professor Jose Fernandez Saez of the Department of Continuum Mechanics. And the main goal is the study of inverse problems for damage detection and detection of cracks, localized damage in one-dimensional structures. As I said before, a lot of research has been developed in the last years on this topic, but still there are fundamental, basic questions unsolved. And for example, there is a well-established theory for detection of a single crack in a beam or in a rod when the crack is small and the crack remains open during vibration. But, for example, few results are known when there are multiple cracks. So there are several cracks in the beam. And so we are trying to extending the existing results, existing theory to this case. Another problem is the following. Most, probably all the no results on crack detection in beams are for small cracks. But in applications, it's difficult to say, to determine exactly when the crack is small. So another line of research is try to extend the existing theory to cover a general case of cracks, not necessarily small. This is another point. However, these are essentially two fundamental lines of research on basic problems. But our interest is also oriented to more applied problems. For example, detection of cracks in rotors, in spinning beams. And here preliminary results show that there are interesting and non-standard behaviors for this kind of systems. Another line of research concerns the extension of these results from one-dimensional to two-dimensional systems, such as, for example, detection of cracks, damages in plates. It's another line of research. A few words concerning our philosophy in order to study this problem. Our main goal is, first of all, to find conditions on the data in order to ensure the uniqueness of the reconstruction of the damage, and if possible, to find closed-form solutions for these problems, or say stable algorithms in order to detect the damage. I have to say that we are working on this. We have worked, and we have find encouraging results on this line of research.